magnetic resonance, we often talk about allowed and forbidden transitions where the selection rule is flipping one spin at a time, delta m equals 1. But we will often talk also about coherences between states separated by more than one spin flip. So-called double quantum transitions or triple quantum transitions, for example, will come in the rest of this presentation. A related, but as it turns out different concept is the idea of correlation. That is, that if you have a density matrix, it can be written out as a direct product representation. It turns out that the expectation value of complex operators, such as IX1, IX2, is given as something different than the direct product of IX1 times IX2. That is only true if you actually have something stronger than the existence of coherences. And then one goes to a further step past that to talk about things like entanglement, where you actually have states such as parahydrogen, or some of the things that have been discussed along in this meeting, where you actually do have an honest-to-goodness superposition for a large fraction of the system that corresponds to alpha beta minus beta alpha. And there are many discussions that took place in the early times of the quantum computing literature, talking about, for example, the difference between entanglement and correlation. Correlations, as we'll see, in general are generated by couplings, although it is possible to have effects from couplings that do not actually generate correlations. Entanglement can be completely different. It was shown by Carl Caves a few years ago that in essentially any small NMR spin system, you can prove there is no genuine entanglement. That is, that at NMR at room temperature, you are near to the identity matrix as your density matrix. And if you are sufficiently near to the identity matrix, you can prove that no matter what you do to the system, you can never have entangled spins. Despite that, NMR quantum computing seems to function as if the spins were entangled. And there is an important and I think very interesting theoretical discussion that takes place about how, if entanglement doesn't exist in magnetic resonance, it can still act like an NMR quantum computer. Okay, so I'm going to start by talking about the applications to magnetic resonance, and I will switch over to optics about halfway through the talk. And so in general, in magnetic resonance, we have couplings between spins which contain bilinear operators. In solution magnetic resonance, we have the scalar coupling, which has this form IA.IB. Incidentally, there was a comment which was made by Ike Chang last night that I didn't object to last night, but it was also, in fact, not something that is quite correct, that when one has this form to the operators, IA.IB, and when you have equivalent of spins, there is no possible spin manipulation which removes that coupling, because this coupling is invariant under rotation. And so it is in fact the case that in many cases you can move them, but this one cannot be moved. And that is often the case which is encountered in magnetic resonance. Dipolar couplings are commonly encountered, for example, I was not here for Professor Kumar's talk, but I'm familiar with the beautiful work that he has been doing on dipolar couplings in liquid crystals, which is an extraordinarily fascinating system. And those couplings have a somewhat different symmetry than the scalar couplings do in solution magnetic resonance, but the same basic effect. One sees a coupling which, as we will see, allows magnetization to be transferred from one spin to another. And dipolar couplings are normally not seen in an isotropic solution. That's because of the results of Bloomberg and Purcell and Pound in the 1940s. Although, as we will see, that turned out to be incorrect. Okay, so in conventional magnetic resonance, we envision the effects that come from either coherences or correlations by looking at two-dimensional spectroscopy. And I have not seen anyone specifically talk about this yet, so I thought I would throw in a simple introductory slide. The simplest two-dimensional pulse sequence is two radio frequency pulses separated by a delay. And so, for example, let's say this delay is set the first time you run this pulse sequence to be 1 millisecond. Then you acquire data for a long interval like this, it's so-called free induction decay, and then you go on and you do the experiment again with a different delay and a different free induction decay. And in doing that, you build up a matrix of data points. That matrix of data points then is presented by a two-dimensional Fourier transform. And here is a simple schematic example of such a thing. This is a small molecule methyl ethyl ketone that has 3 different kinds of protons to it. It has these methyl protons sitting right there, and and these methyl protons there, which are inequivalent in their position, therefore at different frequencies, and these methylene protons. And what happens is one sees a set of peaks that evolved at frequencies that were different in T1 than in T2, and that ends up being a direct measure of either coherence or correlation between them. The reason that happens mathematically is that the density matrix, this is the von Neumann equation, the time evolution of the density matrix. And so the density matrix after a first pulse looks, for example, like Ix. And now this coupling right here, IZ, IA, IZB, allows you to turn this from a single spin into a two-spin term. And then rotations allow you to manipulate it back to be another spin. So as you see from here, in this case where you have this coupling, a coherence can evolve as a coherence on spin A at frequency A during the first time, and on spin B at frequency B during the second time. And this is only possible if the spins actually have a coupling between them. And this, of course, is a very important part of magnetic resonance. It is the way that now we are able to look at large molecules like proteins and unravel the structures of these proteins. One can go on from there and actually look at so-called multiple quantum coherences, highly forbidden transitions. Again, one does now, the prototype is a slightly more complicated pulse sequence, but again, one fixes this delay for the sequence, one fixes this delay for the first execution, acquires a large number of data points, and then you go on and you keep repeating the experiment, just going with different delays like this. And the consequence of that is that one sees forbidden transitions in the spectrum. So let us imagine, for example, a system which is simply a two-spin system that has 4 energy levels associated with it. In magnetic resonance, the transitions that we normally associate as possible flip one spin at a time. They are the 4 with the arrows on them. And so one, in this case, would see a spectrum which looks something like this in a, say, 600 megahertz spectrometer. But by using this sequence, one can actually see forbidden transitions. For example, this transition, which corresponds to flipping 2 spins at a time, which occurs obviously at twice the frequency. And this transition, commonly called a zero quantum transition because the net number of spins changing is 0, 1 up, 1 down, which appears at a very low frequency. It appears only at a frequency that reflects the difference between the 2 inequivalent spins. Now, all of these concepts that I've shown you so far have been known for a very long time. The first cozy sequences and multiple quantum sequences were done in the early 1970s. And I was a graduate student with Alex Pines at Berkeley where I did multiple quantum NMR. And we worked on understanding the mathematical framework that would allow these things to happen. Again, one can go through and simply look at these individual couplings and simply walk through the couplings, and you discover that you produce terms like this green term here, which will flip 2 spins up, or this blue term, which would flip 1 spin up and 1 spin down. And so all of this is quite well understood. And multiple quantum effects are one of the fields that I have worked in ever since the time that I was a graduate student. And so what I'd like to do just to calibrate is to compare what I was doing as a graduate student to what we do today. And I'm taking some representative papers from both of these eras. There are dramatic changes in the complexities of the sort systems that we look at, in the sophistication of the multiple quantum spectrum, in the sophistication of the pulse sequence that one uses to do this, in the sophistication of the solvent. And while I'm sure you can look at this and say that yes, there are very dramatic differences between the work in the left column and the work in the right column, you would also say we are talking about more than a quarter century, and most fields of century. So that would seem to be not so surprising, except that the simple looking things are the things that we do today, and the very complicated looking things are the things that we were doing 20 years ago. And behind that there is a story. It is a story about how the theoretical framework becomes so obviously successful that you forget their underlying assumptions. And you forget more particularly to check those underlying assumptions when something changes, particularly if it changes gradually. In this case, what changed gradually was we went from very small magnets to very large magnets. And any time since 1953 or 1954, the kinds of experiments I'm going to show you could easily have been done showing completely different effects in magnetic resonance than one would have ever expected. Anyone else thought to look for these things because the theory of magnetic resonance was so obviously successful. Now, I would love to tell you that we systematically went through that we found a flaw in the theory and then went to verify it. I would love to tell you that is not true. What actually happened was we more or less blundered into it. That was, we did some experiments which made no physical sense, and then we eventually had to work out why this was the case. So, to give you a calibration, these are the kinds of pulse sequences that we will describe. Professor Chuang showed you the typical kinds of pulse sequences that are used for quantum computing. They're vastly more sophisticated than this. In the 1970s, we were doing sequences vastly more sophisticated than this. I will be showing you things as simple as a 90-degree pulse and a gradient pulse, or a mismatched pair of gradient pulses with two 90-degree pulses. All of these sequences would be trivial to take the theoretical framework that, for example, Richard earns the Nobel Prize in magnetic resonance ago, and Professor Kumar in 5 seconds derived for you why all of these have to give you zero signal, but trust the rest of us who are mere mortals might take a few minutes, but nonetheless it's not so hard to do that. That all of these would have to give you spectra that are completely blank. In fact, if you actually do one of these sequences, you get a very nasty surprise. So this is a test tube of water with a sequence for which you can easily derive you get no signal. In a single shot, you get 1,000 to 1 signal to noise. And so it's completely impossible to miss this effect. And this experiment is so trivial that it could be done on any of 10,000 NMR spectrometers in the world. So now one has to try to understand this. Let's try a bit more complicated. Instead of this water, let's put in, say, water and dimethyl sulfoxide and acetone. All of those are molecules that have only equivalent spins in them, and so the NMR spectrum is 3 lines. And any NMR experiment you could think of would have 3 lines. And this spectrum should be completely blank, but it is not. And the only peaks that show up correspond, for example, to flipping 2 water spins, or to flipping a water and an acetone spin. And notice it's not every possible combination that arises. It only arises if, for example, dimension is water. Only those peaks that would correspond to flipping a water are there, this, and this one, for example, would not be present. And so this is not a random effect, a fully coherent set of effects. Coherent set of effects was extraordinarily difficult for anyone to understand, and very controversial about a decade ago. It leads to some extraordinarily bizarre dynamics. This is, for me, the most fun paper that I ever published. We managed to publish a paper in 2000 which used one 90-degree pulse and one gradient pulse on a test tube of water. And if you would have told me that it would be possible at the beginning of the 20th century to do that, I would have told you you were completely out of your mind. But in fact, it turns out that these systems generate honest-to-goodness, full-blown chaotic dynamics, characterized in true nonlinear physics, positively up and off exponents, and an evolution which is actually quite useful for doing imaging. A former postdoc is now a professor at UCLA who has been following up on this work with the UCLA Medical Center. And so you get these strange dynamics. The signal is highly non-reproducible and experiences the so-called classical butterfly effect that one sees in nonlinear dynamics. Very small fluctuations in the initial state of the system have profound effects on the final evolution. So where does all this strange dynamics come from? It comes from the fact that the fundamentals in 1948 for why you can see sharp lines in liquid NMR is not quite right. So it was known right at the end of World War II that if the NMR spectrum was solid, you have a very broad line. If you have a liquid, you have a very sharp line. And the argument was that you have this dipole-dipole interaction, but the spins are moving around like that, and the dipole-dipole interaction has a specific angular dependence, this 3 cosine squared theta minus 1. And the average of 3 cosine squared theta minus 1 over a sphere is 0, and therefore, as the spins move like this, their dipolar coupling is sometimes positive, sometimes negative, and it goes away on average. Now, that's a very pretty argument, and it rationalizes the raw like scalar couplings in liquids, which you could never see, but it's not correct. Suppose I start with a pair of spins separated, for example, by a millimeter. Now, water molecules can about 7 microns during the timescale of an NMR experiment, and so that is, the interaction is not affected by the diffusion. Now, you may say, why do I care? The double interaction between spin by a nanometer, like this. Why do I care about the one separated by a millimeter? It goes as 1 over r cubed. That difference of 16 orders of magnitude in signal strength. You would think that's perfectly easy to neglect. Unfortunately, the number of spins in a shell of radius r goes as 4 pi r squared. And so coupling falls off as 1 over r cubed. The number of spins rises, the magnetic here from all of the spins in a shell of radius r only falls off as 1 over r. Now further, the magnetic field here from all the spins at a distance is 1 over r, so it converges. Therefore, the field 1 and 3 millimeters from me is of the same size as the field from those spins between 1 and 3 nanometers from me. Now this is a truly very scary argument, because this has to be correct, and it is. For years, they actually give you very sharp lines, and some give you broad lines. So there must be something different going on. What's different known as the angular dependence. That while any of you who have seen an MR know that the way you operate is you take a tube, but a tube, and by coincidence, it also the tongue is about as long as it's wide. So a 5 millimeter to 1 centimeter wide tube, and 5 millimeter to 1 centimeter this way. And because it was found, that gave you better spectra. Well, there's a reason for that. It turns out that if you had a perfectly spherical sample, you'd have exactly the right number of pairs of spins like this, where the dipole interaction is positive, to cancel the ones like that, where it's negative. And if it's not exactly spherical, then the corrections are small, and if the magnetization of the sample is small, as it was in an old magnet, then it's... But that means that's actually a rather fragile argument for saying why this should cancel, and there should be 2 ways to change them. The simplest way would be to make a strange-shaped sample, and people have done such stuff, you find other couplings. But the much more interesting way is gradient pulses. Gradient pulses make the spins at different frequencies, and so they make the magnetization more uniform. And I will not go through the hundreds of equations that one uses to derive this. Suffice it to say that by applying these gradient pulses, you recover the dipolar couplings at a macroscopic distance of your choice, and you end up being able to produce very quantum effects with a typical size that is that is comparable to a scalar coupling. Now, there's some mathematical tricks that also have to be done in order to make this to work. I present this only for completeness. The Boltzmann distribution in magnetic resonance is, of course, written out here in density matrix form. And in general resonance, say operating in the high temperature limit, that is, that h bar omega 0 over kT is 10 to the minus 4th. And so one takes this exponential right here and does a Taylor series expansion on that exponential. This is present in every textbook in magnetic resonance. A few textbooks in magnetic resonance were suspicious there was something wrong with this. One of the classic books by Charlie Slichter has an appendix in the back which goes through the entire appendix to say why this expansion is not correct, and then you go to the main body of the text and it says, and assuming the high temperature approximation we get, because nobody thought anything could have come of this. There is actually a very fundamental problem here. That fundamental problem comes from the fact that if I have 10 to the 20th spins, for example, I will have something like 10 to the 20th terms here in the term that I kept, and 10 to the 40th terms in the first one that I threw away. And so even if each term is smaller, in fact, it ends up being an important contribution. So the bottom line turns out to be that you can show mathematically that if you reintroduce both this idea of the coupling between distance spins to fix the way the equilibrium density matrix is written down, entirely new physical effects arise. And these effects are intramolecular multiple quantum coherence. We'll talk about the difference between a coherence and a correlation. It will turn these systems, while we quite legitimately observe 2 spins flipping at one time, so there are coherences, off-diagonal elements in the density matrix, the correlations between are exceedingly small. That is, the expectation value of Ix1, Ix2 is indeed the product of the expectation value of Ix1 times the expectation value of Ix2. However, even though these individual products are very small, if I have products of the form Ix1, Ix2, and I have 10 to the 20th spins, there are 10 to the 40th such operators. And so even if each one is very small, it can become very competitive with the single spins. And what I'll be showing you are effects comparable to the full magnetization that one encounters with these bizarre sequences that make no sense. So we published 5 papers over the last decade in Science specifically on these various things. from the first observations which showed that you could actually see these things through a variety of imaging methods. We showed in the late 90s that you could see these things in vivo. I'll show you a few images and show you where those things go. That you could enhance brain imaging by looking at these very funny coherences. And I mentioned the chaotic dynamics. Incidentally, there is a large group of people, inspired by Roger Penrose and some of the people who work with him, who believe that these effects prove that the human brain is a large quantum computer. Now, it is entirely true that these effects say it is possible to have spins separated by a macroscopic distance and have coherence between them. It is totally impossible, in my opinion, to have spins separated by a macroscopic distance and have either correlations between them or have entanglement between them in a system such as the human brain, which is sitting at a very high temperature. And so, while if you go to their web pages, you will find this trumpeted as proof that the brain is a quantum computer, they have the intellectual honesty to say, Professor Warren does not agree with this interpretation. I don't really mind what they say. Why is it useful? Well, let's measure spatial structure. By turning on a gradient pulse, I can change the rate at which these spins rotate with respect to one another. And so, for example, for the typical size gradient pulses one might use, say a few milliseconds and say a few gauss per centimeter, I can select to have, say, only those spins separated by 25 plus or minus 10 microns contribute to the signal. And if I double the strength of the gradient pulse, it goes down a factor of 2. If I cut in half, it goes up a factor of 2. And so if I have a material that has structure, I can suddenly measure a two-body interaction. I can measure a spatial correlation, even though these coherences don't have correlation. Again, it's all very subtle, and you have to listen carefully to the terms that I'm using. If you have a magnetization which has structure, we often do talk about things like a two-body correlation function. Okay? And those two-body correlation functions break the symmetry of the sample over particular distances, and yet because we define distance by doing, even if we measure that very clearly. So these are examples of brain images, for example, which we took quite a while ago. The conventional images are sitting at the top. The unconventional images are sitting down here using these multiple quantum coherences. We have gone from animals to humans for exploring this new contrast mechanism. This is an example of the kinds of large differences in contrast that one can see. So this is the case of actually changing the oxygen concentration in the brain. I apologize, that says hypoxia. This is hyperoxia. It is hyperoxia. It is administering O2. And one sees that that change in the oxygenation, which changes the hemoglobin, makes very large changes in these multiple quantum signals over distance scales comparable to the size of the vasculature, even though the relaxation times, the T1s and the T2s, hardly change at all. And so it becomes a nice method of measuring something that's now has physiological importance. Couple of pictures just to help you understand why this measures structure. This is simply something that, this is taking coffee stirrers and water. And when you pick these coffee stirrers and you do these multiple quantum effects, depending on the distance you pick between the spins, you see very different kinds of signals. For example, if I just take a distance that's about 500 microns, the regions that get lit up are regions like this or like this, which are sitting at a intersection between 3 of these cylinders and are roughly 500 microns in size. If I take something smaller, they tend to be the pinch points like this or like that, which get highlighted between the 2 cylinders. And so the regions that get highlighted really do reflect the internal structure associated with them. And that lets us actually look at a variety of tissues. The bones in your body, for example, are not solid rods. The marrow is sitting in them in what are called the trabecula, and they are oriented in a specific direction in space because bone is intended to be stronger in one direction than others. And the sizes of these things are on the order of 100 microns or so, and therefore they're very well suited to this. In osteoporosis, the amount of this anisotropy changes significantly. You cannot find this in conventional magnetic resonance. In conventional magnetic resonance, it's easy to see millimeter resolution. It's easy to see micron resolution. It's very hard to see anything in between. And so one sees differences in the signal reflecting these kinds of things. Okay, let me skip ahead a bit. As you go from coherence into things like entanglement, you start being able to see very different kinds of physical phenomena. For example, you start being able to see the possibility of dramatically enhancing magnetic resonance signals. So with entangled spins, it is possible to add those entangled spins specifically across a double bond, and with the right catalyst and the right molecule, they actually retain their entanglement. And then, if they are added in positions that are equivalent, they can actually be translated to a large magnetic resonance signal. One of the most interesting frontiers is the use of this method, or the method I just showed you, or this method called dynamic nuclear polarization, that allows you to make a reagent which has a very large nuclear spin signal, although only for a short time. You can go out and buy a device now that will take roughly 1 milligram of any material you want, with molecular weight up to about 1,000 grams per mole, and convert it to, say, 25% nuclear polarization instead of 10 to the minus 5th nuclear polarization, and inject it and watch it be metabolized. The trick is the relaxation times are, for carbon-13, in a favorable case, a few tens of seconds, and so you only have a small time to watch things going on. A very intriguing and important application of quantum computing to magnetic resonance would be to take the ideas of protected states and create magnetization in a highly protected state that would last for a time much longer than the conventional T1, unless some metabolic process transformed the molecules in a way that the symmetry was broken. And so it might be entirely possible to use quantum computing ideas to be able to create, in effect, a reagent that is a light bulb that shows some chemistry going on. Okay, I want to switch over for the remainder of my time to talk about laser applications, and in particular, technologies associated with femtosecond laser pulse shaping. So we use laser pulses that have very many photons in them, and so there is no entanglement associated with them. The laser pulses are capable of generating correlations if they are specifically, in certain specific cases, but in most of the cases we will simply be generating coherences. And this is a technology that we invented about a decade back. You notice the chairman of the meeting sitting here is one of the co-authors on that paper, that allows you to manufacture tailored laser pulses with roughly 1,000 bits, of resolution across the spectrum. So you can make an exceedingly complex optical waveform, basically any waveform you want. And this and some of the other technologies have now been used in a variety of groups over the last decade, for example, for this field of quantum control. I have personally not been a great favorite of quantum control over the course of the last few years. And the basic reason for that is that my feeling is that quantum molecular control, is very interesting if you can achieve one of two goals. If you can make gram quantities of some reagent, which you couldn't make it another way, or if you could take the waveforms which actually come out in the quantum control process and then learn something about the molecular dynamics. Now, you will be some people later in the meeting who are certainly looking in that direction, but the vast majority of what has been published to date more or less uses the waveforms that come out as a black box and say it's much too complicated to understand what these things are really doing. And so we've taken a very different tack. We asked what kinds of systems can we use relatively simple pulse shaping and really understand something new about the dynamics or some new molecular system. One of those is detecting anthrax. So anthrax is a spore, and spores are about 20% by weight of the molecule calcium dipicolinate. Now, for those of you who are not chemists, this is picolinic acid. And to get to dipicolinate, you add in a carboxylic acid group right here. And then the calcium salt, of course, is what makes the protons off. You can look at this molecule and say it looks somewhat like an amino acid, but it's not an amino acid. And you can imagine, first of all, how something biological might make this, and second, how something biological might not want to eat it. And so, in fact, spores protect themselves by creating this coating for this calcium dipicolinate, and then can be preserved for centuries or millennia and be resuscitated back to spores. But this molecule has some bizarre resonances in its Raman spectrum. regions that are not expected to be strong in a conventional Raman spectrum. For example, this characteristic splitting sitting right here, and such that what we call BDL Raman spectroscopy. BDL stands for big dumb laser. In other words, the simplest thing you could do. Blast the living daylights out of a molecule and then see how much signal comes out. Comes remarkably close to being a useful method to detect it. If you use coherence, specific shaping for the laser pulses, you get considerably better. So this just shows you simple examples of some of the first work that we did with shaping laser pulses to go through and alter the amount of the Raman spectrum that one produces from dipicolinonic acid. And let me give you an idea of where the current state of the art is. So we have been able to calculate that taking a laboratory size laser, projecting it off to a kilometer distance, we know roughly how much energy could be deposited there. There are quite a variety of groups who do those sorts of atmospheric propagation experiments. Collecting back the Raman signal at a mirror at your detector, which is 10 centimeters in diameter, that you'd be collecting back 100,000 photons per second at concentrations that you would actually be worried about for a real biological system. And with some of the methods I will be showing you in a moment, which take advantage of pulse shaping as well, those signals can be enhanced by 3 or 4 more orders of magnitude. So the consequence of that is that you are able to actually predict methods that realistically fit very nicely into the spectrum of detection methods that are useful for anthrax. By which I mean the following, that if I gave you a powder and you wanted to know for sure there was anthrax in it, you would do biochemistry. You would do what's called real-time PCR. And in 45 minutes, you would know with 99.9999% probability what it was. Unfortunately, 45 minutes is a long time if, for example, this is an envelope sitting in a mail room. And so the way it's really done in post offices around the world is they simply have a laser sitting up at the top, and that laser is, for example, a YAG laser, and they simply look for light scattering. And the light scattering can be induced by talcum powder or by things that are non-biological as well. So what you really like is something that fits in between, something that has a modest molecular specificity. We can't tell the difference between anthrax and Bacillus subtilis and Bacillus thuringiensis, but we can tell that it is a spore, and we can get an answer very quickly. And so that has a tremendous value in fitting into this combination. The second thing that I wanted to talk about in terms of optics is understanding the optical spectroscopy of you. Now, you are opaque, or at least if you look at the person next to you, you will say the person next to you is opaque. But that is because your eyes are tuned to a specific small range of wavelengths. And outside of that range of wavelengths, actually, you are not opaque. So the absorption coefficient here is plotted not in reciprocal centimeters as in the spectroscopy unit, but as in 1 over centimeters for penetration depth. That is, for example, if we sit out here in the UV, where these numbers are 10 to the 4th to 10 to the 5th, that means protein, that's generically all of the biological molecules in you that are important, cause light to be absorbed over a distance of about 10 microns. Okay, so in other words, at that wavelength, UV light penetrates about 10 microns into you. Through most of the visible region of the spectrum, you and I are dominated in our coloration by melanin, by hemoglobin, and deoxyhemoglobin. And most of the differences between skin color, in fact, are simply the amount of melanin and sometimes 2 different kinds of melanin that are produced. But if you add those numbers together, you typically get something like 10 to the 3rd per centimeter. And so you look 10 microns into one another and that's it. And so it makes sense that we think we are okay. But organic chemists know it's very unusual to find molecules that absorb in the visible. And if you go into the near-ionic, it's even harder. Down here, these numbers fall off dramatically before they start rising again as you go up into the infrared. Let me blow up this region for you a little bit. And look, for example, here around 800 nanometers. So at this point, the sum of those coefficients is about 0.1 per centimeter, which means light goes 10 centimeters into you before it gets absorbed. As I will show you in a moment, you can put a transmitter right there and a receiver right there, and you can see the light just fine. Furthermore, you start getting important molecular signatures. Notice at 770, for example, the deoxyhemoglobin is an absorption, which is not sitting in the oxyhemoglobin spectrum. So if you go with a femtosecond pulse, or if if you go into a variety of wavelengths, you can actually measure tissue oxygenation state, which is a very important molecular parameter. And people do these things all the time. This is an example of an older device. I'm putting up the older device rather than a new one because it's easier to see. That has 8 diodes and 8 detectors. What one does is modulate each of these diodes at a different frequency. And so you end up getting, in this case, 64 source detector pairs where you can go through and invert the signal coming through. Now, this works very well, for example, for looking at very young infants. We're looking at oxygenation level in the brain. This is actually a rather deceptive picture. This picture, which came from the manufacturer, shows this beautiful young lady with a full head of hair which contains a lot of melanin in it, and therefore, in fact, this device would not work very well on this lady. And so, in fact, this device works much better on natural blondes or middle-aged university professors. It's been known for a long time that these things actually work, but they work poorly. And they work poorly because although the transmission distance, the transmission distance is 10 centimeters, the scattering distance is about 100 microns. Okay? And so, in the case I just gave you, putting a transmitter right there and a receiver right there, it makes no difference to point the transmitter with the receiver. It's just a completely incoherent flow of light. So we want to ask, is it possible to do better than that? Is it possible to do microscopic resolution, deeper resolution? And now we start having to invoke ideas of coherence and things like multiphoton effects. So the most important of these effects that has been done over the years is two-photon fluorescence microscopy. There were a group of people in the early 1990s who realized that when you went in with a high sapphire laser at 800 nanometers, you could force molecules to absorb 2 photons at a time. Because it's absorbing 2 photons at a time, the probability is proportionally intensity squared, and therefore the scattered light doesn't give you much signal. And so you can get down considerably deeper into tissue. You can get down to the order of a millimeter. Here are a couple of examples of such a thing from the home-built microscope that we have, but there are commercial two-photon fluorescence microscopes. This is merely using a sample that has some fluorescent beads. This is using a sample which is a melanoma. And the reason this looks like such an ugly-looking image, I'll show you in just a second. So the idea is, again, I'm going with the laser that has very short pulses. These very short pulses force molecules to absorb 2 photons at a time. But because they're on for a short time and off for a long time, the average power is low. So since the signal depends on intensity squared, you get polarization, you get chemical contrast. But the most important limitation is the vast majority of the things that you do not fluoresce. Okay? And therefore, there are some molecules you can get to, the vast majority of molecules you do not. And so it becomes very restricted to see what you can actually pull up from such images. Okay, I guess before I go too much further, I should point out that while you might think it's crazy to apply a laser to somebody's skin, you can easily show what the damage threshold is. And the damage threshold, either for a continuous laser or for these very short pulses on or off, is about 25 milliwatts. And so, if you have ever asked yourself the question, when the professor gets a little bit tired and is giving a lecture and as the laser pointer sweeps it around the room, should you panic? Okay? Well, the answer is that's because those pointers are limited by law to 5 milliwatts. They're about a factor of 4 away from the point where they actually cause damage. You may think that's a very low safety threshold. If you think that, never take acetaminophen, Tylenol in the United States. Because while acetaminophen is the safest painkiller you can take in its normal dose, it is disposed of by specific enzymes in the liver, and if you saturate those enzymes, you will die. And the lethal dose is about a factor of 3 to 4 more than the dose that's the normal dose that you actually take in order to get some effect. So there is often a good reason why they tell you a maximum dose that's sitting on those non-prescription drugs. In that case, there's a really good reason. Okay, so two-photon absorption images would overcome the disadvantages that I had associated with fluorescence, right? Because every molecule absorbs if you go to short enough wavelengths. In many cases, they'll absorb at long wavelengths. And in that case, you can actually go deeper into tissue. So you have this advantage of getting better spatial localization and chemical contrast and deep penetration, all these other good things, except you have a problem. And the problem 1 photon and 10 to the 6th will be taken up by 2 photon absorption. And the rest of the photons will be lost either to scattering or to linear absorption. But in any case, it's the same thing that's happening. It's simply that the light is lost. So how do you tell the difference between those effects? And this is where pulse shaping comes in. The simplest kind of pulse shaping simply takes advantage of the frequency structure associated with a mode-locked laser pulse train. If I have a conventional mode-locked laser that's a picket fence of pulses, it also produces a picket fence of pulses in frequency with perfect spacing. If I put an amplitude modulation on this, I create sidebands. And if I have 2 photon absorption as well, the big pulses are attenuated more than the little ones, and therefore it creates new Fourier sidebands at frequencies which could never be created by a linear process. And therefore, by simply detecting those frequencies, I can see the needle in the haystack. These are specific examples of imaging human melanomas. I'll show you a bunch of images, but let me also give you the motivation. You show up at a doctor's office with 100 moles, and the doctor has to try to figure out which one, if any, of these have to be removed. No, there's no way he can look more than a few microns deep, because they're heavily pigmented. What he would really like to know is, for example, how deep is the mole? Your skin is 1 millimeter thick in most places. If a mole is more than 1 millimeter thick, it has penetrated the dermis and it is trying to go someplace else. He would really like to know that. The melanocytes, which actually generate the melanin, have a nice uniform distribution in ordinary benign moles, and they have an unusual distribution in melanomas. If you could see that distribution of melanocytes, that would also tell you. The only way they find that now is by cutting them out and slicing them in half and looking at them in a microscope. But it is obviously not feasible to do that with hundreds of moles. Okay? We can look a millimeter deep into a mole that looks black from the surface because we're using infrared light where it's not black. We can get microscopic resolution a millimeter deep. So we get structures, for example, like the kinds of structures that you see here. The light level's not quite perfect. Let me see if I can just find a slide where the light level seems a little better. Yeah, I hope you can at least see this. So this is an actual two-dimensional structure of one of these where the melanocytes, which are actually generating the melanin, are sitting right in here. It's the region that's highlighted. And we do things like looking at the quantum yield, we're looking at the quenching and so we can actually extract data sets in short periods of time, a few minutes at this point, which give the sort of clinical information that the doctor finds useful. And we can do these things in vivo as well. So these are all melanomas where you actually see the bright red spots here are the places where there's the absorption that was actually generated by the melanosomes. And this green undifferentiated stuff is just the normal fluorescence, which doesn't give you any interesting information. There are many other molecular targets you can get to. You can get to hemoglobin, deoxyhemoglobin, you can get to various cytochromes. We're working on all of these at this point in conjunction with the people at the medical school. A big part of the reason I moved is because Duke has one of the best medical schools in the world, and they have the clinical collaborators who are very helpful for me to work with. To give you an idea of how sensitive this method is, this is the very best data in the literature on 2-photon absorption of cytochrome. And you can see these error bars. They're written in Goldberg-Meyer units. They're typically about 300 Goldberg-Meyer units. These are the error bars of what we are doing with laser pulses with 1/1,000,000th of the peak power. And the error bars are by a factor of 100 small. That's a pulse shaping effect. There are more interesting pulse shaping effects that happen if you can go through and you can actually produce specific kinds of tailored pulses. For example, suppose I start with a pulse that has a hole in the middle of its spectrum. With the hole in the middle of the spectrum, the Fourier transform of such a pulse must have an intense and short part and a weak and long part such that this area and that area exactly cancel. If I have a nonlinear process, I'm going to show you two different lines. In fact, you end up getting the hole refilling. The first process I'm going to show you is self-phase modulation, which was also discussed in the context of Neil Gershenfeld's lecture yesterday. It's one of the processes that's involved in making soliton pulses and such things. But I'm going to not worry about this at the level of the inside the laser and the lower powers that we would actually have for tissue. So self-phase modulation means the index of refraction changes here, which means you get a little bit of phase shift here, and so this no longer cancels that, and suddenly there's energy sitting in the spectral hole. Similarly, if I have two-photon absorption, same thing happens, except now energy is lost from the big pulse, and so now this thing is negative sitting right here. So if I can measure the phase of, so there are two things I can do. First, if I have a hole here, non-intuitive as it sounds, I create a laser pulse which is dark at a wavelength, and absorption makes it bright at that wavelength. That's very good in terms of non-background processing. But if I can measure the phase here, I also measure the difference between these different nonlinear processes. Two-photon absorption and self-phase modulation give you very different kinds of signals and different structures in tissue. We can do that with the technology we have for femtosecond pulse shaping. We manufacture laser pulses with a hole which has a pedestal sitting in it. And because we use these acousto-optic pulse shapers, we can run at, say, 250 kilohertz, and every single pulse had a different shape. So for example, the first pulse can have this phase 0, the next one phase 10 degrees, the next phase 20 degrees, and so forth. And thus we directly pull out the phase of the refilling, and we do it fast compared to any physiological processes. This is only a very simple kind of pulse shaping. One can imagine extensions. I've told you we could do 1,000 pixel pulse shaping with the device that's sitting here, but this already gets us a lot of interesting results. So this data came out in Optics Letters a couple of months ago, and since that time we've actually gone on and seen that, in fact, with different biological systems or different systems like rhodamine 6G, the signals dramatically differ from one another. And so you really have the possibility of extracting modest laser powers with molecular signatures that tell you what's going on. Okay, so I'll conclude. This idea of exploiting the coherence which is generated in an optical field, taking advantage of the difference between merely having a spectrum that has a hole in the middle of it, which in fact I could do if I had an LED, and having something that is coherent, in other words, an optical field where everything actually comes in phase, gets you the possibility of exploiting effects which allow you to penetrate deep into tissue and do a variety of other applications you've heard about. Going from coherence to correlation allows you to measure some specific things if you have individual molecules with couplings between them, but you can measure spatial correlations even if you don't have coherences, you can actually measure spatial. And entanglement gets you a few other interesting concepts. I showed you one in magnetic resonance. I'll leave you with one interesting additional conjecture. If you could make a good entangled photon source at 800 nanometers and applied it to the scattering material, and so I had pairs of photons at 800 nanometers, then if I put them in here, and if one of the photons showed up right here, the other photon would have to show up here as well. And therefore, the number of paths that it's allowed to occupy in going through is decreased. And so the spatial resolution that you acquire from using entangled photons in microscopy is better than the spatial resolution you acquire from unentangled photons. My colleague Marlon Scully, who we collaborate with in the Anthrax project, has actually put together a bunch of PRLs which show in principle factors of 10 resolution using idealized, extremely highly correlated photon sources. And one could imagine, in fact, this is actually quite possible by taking advantage of entanglement between individual photons. So I think there are some intriguing applications of all of these ideas, which all touch very much on the quantum computing community in a variety of spectroscopic methods. And so with that, I simply